All right, ladies and gentlemen, here's that little bit of in-depth or reminder, however you want to look at it, because how and why this stuff works is pretty important, because we don't just make this stuff up. So when I have some, and I'm not going to work through all of this all the way. What I'm going to do is I'm going to show how in the world we got to something like this, or we knew to subtract, or we knew to multiply those. Okay, so we have to remember that 3 squared is the same thing as 3 times 3. We also need to remember that 3 to the 6 is the same thing as 3 times 3 times 3 times 3. And I said this in the video, but it's always good to see it, okay? So when I have 3 squared times 3 to the 6, I could actually substitute each of these in. This one for 3 squared, so I have 3 times 3. And just to be able to go back to the original, I'm going to change this symbol to the old school multiplication, just to be able to differentiate between the two groups that we substituted for. So this is not x like unknown, this is x like multiply for an example. So then I'm going to take this group right here and say 3 times 3 times 3 times 3 times 3 times 3. And then I just have to count it, because since they're all multiplying, this is that has to translate to the same thing as 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 3s being multiplied, and that's how I got there. So the shortcut was we could sit there and say, well, we have 2 here and 6 here, and adding those together became our 8, okay? So the same thing happens for division. In the division, this is saying we have a -4 times a -4. In the numerator, because this is the same as negative, that was weird. Every once in a while it likes to do that. -4 squared. And then -4 to the 7th, I think we can see it. I'm not going to write all of it. It's -4 times -4, and there's going to be 7 of those, times -4. And there's a total of 7 of those, okay? Well, the thing is, when you have the same factor in the numerator as you do denominator, so we have -4 times -4 for our 4 squared. We then have a denominator of -4 times -4 times -4. I think I'm going to run out of real estate. 1, 2, 3, 4, 5, 6, and then times -4. All right, so this is going to cancel here. And remember, when we cancel common factors, they don't just disappear and go to 0 or anything. They become 1, so it's the same thing as 1 times 1, which is 1. That's all that's left in my numerator, but then I have 1, 2, 3, 4, 5 of these guys left. So we have 4 negative quantity to the 5th. Sorry, I said that backwards as I was writing it. My brain just did it that way automatically. All right, so this was the example of B. This was the example of A. And so now we get an example of C. C is saying that we have z to the 4th a -3 times. Well, I could go ahead and say that's the same thing automatically of z to the 4th to the 3rd. Well, I got to remember that means it's 1 over z to the 4th times z to the 4th times z to the 4th. Now, I don't have to write all those out because we already showed by example A here that this is just the same thing as the 4 plus the 4 plus the 4, and when we're adding the same number to itself, we just count how many times it is and multiply it. It's the same thing. So that means that this is the same thing as z to the 4 times 3. Oop. I'm just going to erase that part. Holy cow. I don't know what my brain was thinking there. I know what I was thinking. z to the 4 times 3, which means my final answer is z to the 12th. Why is there a 5 here? That's supposed to be a 3. Oops, a little too much. There. Okay. Well, welcome to the bonus features. Anyway, z to the 4 times 3, that's going to be z to the 12th, which is what we got in the original answer. So there's a lot more to show to try and bring you up to date on the things that should have already been instructed back in pre-algebra before, but this is all the workings behind to be able to allow the properties. And I like to think of properties like shortcuts. They're not extra things to learn. They're based on what we know in math. They allow us to do things quicker because we can skip all the steps like writing all of these 3s or all of the -4s and thinking about it that way. We just have to know that if it's the same base and it's multiplying, we're adding the exponents, because this works 100% of the time no matter what the base is and no matter what the powers are. Same thing when we have the base and we're dividing, or the same thing when we have a base to a power to a power. So we have rules for those. We call them properties, and those rules are actually telling us what the shortcuts are. So we don't have to do all the work I have in purple. I can just do the work that I did in black, the work I did in green, and the work I did in orange, because the work in purple is true all the time. So welcome to properties, welcome to why they actually work, welcome to just why we teach them, and we've been teaching them for quite a while, like the commutative property, the distributive property, the associative property, things like that. They're shortcuts. As soon as you know how they're working, they're actually shorter ways of doing work. So if you got any questions, let me know. This, again, was an extra video, so I'm still glad to talk about it, but this is more of a mindset and understanding of it. The real trick is getting to know the properties so that when you see a base or a like base to different exponents or even the same, you just add the powers. When you're dividing, you subtract them. And when you got a power to a power, you multiply those powers.